And now you can see that this condition is actually no longer valid. So even though these two are still valid, this one is not valid. We have to update our have count. So our have count was 3, but now index 6 all the way to index 12, that's a lopping and making it smaller, but also keep going until it's no longer valid anymore. So we pop an O. Let's remove a D. So we can remove that E as well. Now you notice we're still valid. We have a B. Lastly, that's less than how many we need. So we have no more characters left. We move, and we have the input string T, which is problem. And I'm gonna have empty. And the first thing I want to do is initialize our count T map, because we know this map actually isn't going to change at all. So for every character in string T, I'm going to add 1 to it, but the value I'm going to get, I can't just do this because it's possible that C hasn't even been added to count T yet. So I'm going to do some Python stuff. I'm going to use the function get, which is good for this. So I'm going to get C. I'm going to get the count of C. So if C exists in our map, it will give me the value that's stored in here. If it doesn't exist, I can put a default value, which is going to be 0. So if it doesn't exist, this function will return 0. So that's just a way that I like to handle this case. So now that we've initialized the count of T, we can have our variables have and need. So we know have initially is going to be 0 because we have 0 of the characters we need, and need is going to be initialized to the length of count T, because that length of count T gives us the unique characters in the string T. And then I'm just going to start iterating through every character in S. So I'm going to use a right pointer for that. The R is going to tell us the right boundary of our current window. So I'm going to get the character that we just reached, which is S at index R. So I'm just going to put it in a variable C. So with C, we know we can update our current window. So I'm going to do window of C and add 1 to it for the character that we just reached. And here I'm basically doing what I did above. If C has never been added to window, we're just going to return 0 with this function. So 1 plus 0, we'll put a 1 here. If it does already exist, this function will get us the count that was stored in here. So we're updating our window, we're adding the count to it. Now we want to know, does this count completely satisfy what we were looking for? Does window of C equal exactly count of T? That means we just satisfied a condition for the first time. But one thing I also want to check before I check this is that C is even a character in count T. So if C is in count T and this is true, because we know we don't actually care about the characters that aren't even in the string T to begin with. And we know if this is true, we can update our have count, so we can increment it by 1. This means we just satisfied a condition. So now what we want to know, does have equal need exactly? So are they actually equal? If that's true, I'm going to run a loop, and I'm going to show you why it needs to be a loop. So if we actually met the condition, let's update our result potentially, right? So if we found a new minimum result, let's update. So this actually reminds me that I didn't even set a result. So let's set our result and our result length. So initially, we know our result is going to be a pointer, like a left and right pointer. So I'm just going to give it a default value of -1, -1. And for the result length, I'm going to put float infinity because that's a good default value in this case because we are looking for the minimum string. So any value will obviously be less than infinity. And I'm also going to initialize a left pointer because we know R tells us the right pointer, left pointer will initially be set to 0. But so now we can actually update our result. We know the condition has been met. So if the current length of our string, which is going to be R minus left plus 1, this is how you just calculate the size of our current window. If it happens to be less than the current result length, which initially starts at infinity, so this will definitely execute at least once. If this is true, we can update our result, which is stored over here. So we can set our result to left and right. This is the window, and we can set our result length equal to the size of this window, which we just computed above, but let's compute it again. This is the size of the window. And just like I showed you in the drawing, while the condition is met, we want to keep shrinking from the left. We want to make this string as small as it can possibly be. So let's pop from the left of our window, right? Let's try to minimize it. So I'm going to remove the leftmost character from our window map. So the leftmost character is the string at index left, right? And from this, I'm going to decrement it by 1. So now, since we removed a character, it's possible that our have and need condition is no longer met. So I'm going to do something similar to what we did up here. I'm going to check if this character S of L was in count T, meaning it's one of the characters that we need to satisfy our condition, and if somehow right now, for the first time, that we took this character from our window and now the count is actually less than the count that we need, which is present in count T. So now if by removing a character we just made it less than what it needed to be, what we did is we just took our have and then decremented it by 1. Right? So this is just a part of removing a character from the left. We update our map, we update our have count if we need to, and lastly we take our left pointer and increment it by 1 because of course we have to shift this by 1 if we're removing a character from the left of our window. So now after we do this, we're going to potentially check the have and need condition, and it might be true, it might not be true, and whatever it is, the loop is going to execute when it needs to. So this is all we're doing. We're taking characters, adding it to our window map, checking if the condition has been met, updating the window accordingly. That's all we need to do. By the end, the result, if it exists, will be stored in our result variable. So our result pointer, we can put it in left and right. We can take result and extract it into left and right. These pointers in this case, these new left and rights will tell us the result. So what we can do is say return from string S going from pointer left all the way to pointer right, but we need to add 1 for the off by 1 error. And we're only going to do this if the result length has been changed, meaning it's no longer infinity, because we know it's actually possible that a result does not even exist. If that's not true, if a result doesn't exist, we know we have to return an empty string. So there it is. This is the entire code. I'll probably have to link this in the description.
What is going on here? Oh my god. Hey Nick, studying for your interview? Yeah, I am, but I'm really nervous. I mean, I can't even invert a binary tree, or
I can't even implement a binary tree. It's gotta be some level, right?
reverse a linked list. Wait, when's your interview? I think it's in like 5 minutes. Okay, you know what? You're probably gonna fail, but if you ever get stuck, just throw a hash map at the problem. Throw a hash map? What? Okay, it's time. Hey Nick, I'm Nick with a K, and I'm a senior software engineer here at Faces on Google Appflix. I'm just going to send over a coder pad and then we can get started. Yep, sounds good. So here's the problem. Given an array of integers nums and an integer target, return indices of the two numbers such that they add up to target, and you can just assume that there will always be a solution. Huh, what an easy problem. I did this last night, but I'm going to pretend I've never seen this before. Interesting. Yeah, so I guess my initial approach would be to use two for loops and then iterate through the array, checking whether the sum of the current number and each of the numbers in front of it adds up to the target. Yep, that sounds like a good start. Do you want to code it up? Yeah, sure, no problem. I'll start coding it up right now. And then in the event that I read through the array before. Interesting. Yeah, so I guess my initial approach would be to use two for loops and then iterate through the array, checking whether the sum of the current number and each of the numbers in front of it adds up to the target. Yep, that sounds like a good start. Do you want to code it up? Yeah, sure, no problem. I'll start coding it up right now. And then in the event that there are no solutions, then we can just throw an error. Yeah, so that should work, and its time complexity is O of n squared, because for each element, we're looping through the rest of the array to find its complement, which takes O of n time, and also the space complexity is O of 1. Okay, that seems alright, but it's a bit slow. As you mentioned, it's quadratic in time. Do you think you could make it even faster? Of course. I knew this was coming. Yeah, so we can just sort the array first, and then use a left and a right pointer, and move those towards the middle of the array accordingly, based on whether the sum is less than or greater than our target. And so the time complexity of this solution would be O of n log n, because we array accordingly. I knew this was coming. Yeah, so we can just sort the array first, and then use a left and a right pointer, and move those
Sort them right first and do a 2 pointer.
those towards the middle of the array accordingly, based on whether the sum is less than or greater than our target. And so the time complexity of this solution would be O of n log n, because we need to sort the array. And then we also have just one pass through the array, which is O of n. And also our space complexity will be O of 1. Yes, I did it. I definitely passed the interview. Well, yes, this is a bit better, but it's still kind of slow. I want you to think of a solution in linear time. What? Linear time? I thought I already got the off. Optimal solution. There's no way you can make it even faster. Well, I guess we could maybe instead of doing what we had before, we could instead do Nick, we only have about 5 minutes left, so if you can't think of a better solution, don't worry about it. Come on, Nick, think. Think! What could we do? Man, I'm so stuck. Wait, stuck. If you ever get stuck, just throw a hash map at the problem. Throw a hash map at the problem. Hash map, hash map, hash map. That's it. I'll use a hash map. Yeah, so we can use a hash map. We can just iterate through the array and find the complement of each number. And if the complement already exists as a key in the hash map, we can just return the corresponding value, which is going to be an index, along with our current index. And the sum of the two numbers at those indices will add up to our target. And if the complement does not already exist as a key in the hash map, then we're just going to store our current number along with our current index in our hash map. Yep, that sounds like a pretty good plan. We only have a few more minutes though, so if you could code that up quickly, that'd be great. Yeah, sure, I can start coding it up now. And then again, as I mentioned, in the event that the complement does not exist in the hash map, then we're just going to store our current number along with its index in the hash map. So that should work. And in terms of time complexity, we're only looping through the array once. And since hash maps have constant lookup times, this algorithm is simply O of n in time. And our hash map would store at most n elements, so it's going to be O of n in space. Yes, I finally did it. I definitely passed now. Perfect. Well done, Nick. That concludes the interview for today. Keep an eye out for an email to schedule your next interview. All right? Have a nice day, Nick. Thank you. You too. Wait, did he just say next interview? There's more? Say next interview. Nick. Thank you. You too. Wait, did he just say next interview? There's more?
I'm glad I didn't get fired.
It was definitely like a lot of pressure that I put on myself.
I was ready to quit school.
Why is it so hard to get a job? Should I do something else?
I was like, oh crap, I shouldn't even be here.
Definitely more failed interviews than ones I've passed.
I changed it to like the wrong value. 20,000 payments didn't go through. It's that time of year again. Intern season. Which means that LinkedIn's about to be flooded with people flexing their big tech internships and cool startup jobs that they have for the summer. You might have seen one of these posts before and thought, he's going to Meta and Google? Man, these guys are built different. But what you don't see are the failures, rejections, breakdowns, and the nights where you genuinely think, maybe I'm not cut out for this. So, for the third year in a row, I went to Hack the North, Canada's biggest hackathon, to ask interns from companies like Apple, Meta, and Twitter about the lowest points in their journey and how those moments actually helped them succeed. And they all go to the University of Waterloo, where doing 5 to 6 internships is actually not unusual at all because it's part of the degree requirements. So stick around because this is the messy, unfiltered side of success that you won't see on LinkedIn. All right, we are here with
Angel.
What do you study and what year are you in?
I study computer science and I'm in 4A.
Victor, computer science, and I am in my last year, 4th year.
My name's Emily. I studied systems design engineering and I graduated 2023.
Daniel Zhu, computer engineering major, and I graduate in 2026. We're actually wearing the exact same outfit. This is the craziest coincidence.
So what's your name, school, major?
My name is Nick. I go to Waterloo for computer science. I'm in my 4th year.
Most recently, I was at Stripe, and then before that, I was at X, or Twitter.
I was an intern at Ramp this summer. I interned at Snowflake after.
I've been at Uber as a APM, an associate product manager for the past year.
I spent the summer in New York interning at a database company called Cockroach Labs.
So this summer I actually completed my last internship at Meta, and then previously at Microsoft, Apple, and Bloomberg.
Damn. Have you ever failed a tech interview? I have failed.
using it, and time complexity is going to be around n.
Hey everyone, welcome back, and let's write some more neat code today. Let's look at a sliding window problem, a hard sliding window problem, sliding window maximum. The statement is pretty straightforward actually, so we're given an array of numbers, and we also are given a number k, which is going to represent the size of our sliding window. It starts at the very left and then works its way to the right, and so since it's size k, there's only going to be k numbers inside the window, and for each position that the window is in, we want to return the max value. So you can see that this is our input array, and our window is going to be size 3, so this is our first window, and the maximum value is 3. So then we see, and then we add a 3 to our output array. So the output is going to be an array. Next we see that this is the next position of the sliding window, and the maximum value in this case is still 3. So we put a 3 in our output. And the next position we see that this is our window, the maximum value is 5. So we put a 5 in the output. Now, you might recognize one solution to this problem immediately. For each of these windows, why don't we just scan through the array, right? Like, it's pretty easy to find the maximum in an array, right? Like, if we had 1, 2, 3, we just check every value and see, okay, this is the maximum. And then we just shift our window by 1 into the next position, right? And we keep doing that until we're done. Well, the time complexity of this is going to be roughly, since the size of our window is k, how many windows are we actually going to have? Let's say the entire input is length n. In that case, we're going to have roughly k times n minus k. That's how many windows we're going to have, right? And so this is going to be our time complexity. But I'm asking, is there a better solution? Can we actually make a linear time solution where n is the size of the input array? And the answer is yes. And I'm going to show you how to do that right now. So I'm going to show you the best solution, but one thing you have to notice first is this. So let's say this is our input array. We have 4 numbers and our window size is going to be 3, so k equals 3. Notice how these values are in increasing order, right? 1, 2, 3, 4. Okay, so we notice that. Now look at our first window. We have 1, 2, 3. We see that 2 is greater than 1. We see 3 is greater than 2. Now that's good. And so we scan through every element. 1's not the max, 2's not the max, 3 is the max. So then in our output, for the first value, we're going to put a 3. Okay, and that's great. Now we shift our window to the next position. So now I'm literally just going to repeat that process the brute force way. Now I'm going to check 2, okay. Now I'm going to check 3, 3 is greater. Now I'm going to check 4, 4 is the greatest. So we add 4 to our output. And so then we're done, we have our output, but we just did it the brute force way. But do you see the repeated work that we just did? As soon in our first window, we saw 1, 2, 3. We know 3 is greater. So we basically eliminate 2 and 3. And then when our window is at the next position, it's over here, right? 1 is no longer a part of our window, so we don't need to worry about 1. What about 2? Well, 2 is inside of our window, right? It's at the leftmost position. But since we know that this 3 is greater than the 2 anyway, why would we ever need to look at the 2 ever again? It's never going to be the maximum. And let me just make it even more obvious. Let's say our window size is 6 and this is our input array. Okay, so for our first window, we have to check, okay, the 1, another one, another one, another one, another one, and then a 4. So the 4 is our max. That's great, so we can save that. And then we shift our window to the next position and see we're repeating all that work over again, the 1, 1, 1. As soon as we see this 4, we know that these elements, as far as we're concerned, are useless to us. We never have to look at them again. They will never be the maximum inside of our window because our window is going to continue being shifted to the right position, and the 4 is still going to be in the window even after these elements have been eliminated. And so the data structure we're going to use to eliminate these values is a DEC or a DQ. And I'm going to show you the algorithm. And just to repeat myself, basically what I'm saying is if we have a window and we see a value that's greater than values that are previously in our window, then we can eliminate those values from our window. And so I'm going to show you the algorithm, and what you're going to notice is that the values in our DEC are always going to be decreasing order. So this says decreasing. So we know our sliding window is initially size 6, right? K equals 6. So we're going to take the first one, put it in our window, the second one, put it in our window, and then just repeat that, right? We have 5 ones. We're going to add all of them. And then we get a 4. So since 4 is greater than the value at the top of our DEC or at the rightmost position of our DEC, what we're going to do is we're going to pop this value off. What we're going to do is pop the top of the DEC, right? And now we're going to make the comparison again. We see there's still a 1, so 4 is still greater than the top of our DEC, so we're going to pop. We're going to pop this, we're going to pop that, we're going to pop all of them, and after that, we're going to add the new value 4. And so what are we going to add to the output? So we have an output array. What value are we going to add to it? Well, the leftmost value, and in this case we only have one value, is going to be what we add to the output, so a 4. And so we're done with this comparison. We don't have to look at it again, and we don't even have to consider these elements anymore. And now we shift our window by 1 position. So we're introducing a new element, 5. So before we add the 5 to our DEC, what do we have to do? We have to check, is 5 greater than the value at the top of our DEC? It is, because the top value is a 4. So why would we ever consider the 4 as the maximum value ever again when we know there's a 5 right next to it? The answer is we don't have to, so we remove the 4 from our DEC. And then we can add the 5 to the top, and then we know that there's only one value in our DEC, and it's also the leftmost position. We are going to add that to our output, and now we're done. This is our output. But what's the time complexity of this algorithm? First, we took each one, added it to our DEC, right? We did that for every single value. That was expensive. And then we also crossed out. We had to remove every single value from our DEC. But adding and removing, we know adding and removing is an O of 1 operation to our DEC, and we had to do that for every single value in here potentially. But that's still O of n, right? The result is O of n, which is why this is a really good solution. And I'm going to show you one last example. And by the way, this is called, the type of problem this is called a monotonically decreasing Q. And the reason is because our Q is always going to be in decreasing order, which this next example is going to demonstrate. And the reason we're using a queue rather than a stack is because we want to be able to add and remove elements from the beginning in O of one time. But not only that, as our window shifts, like for example, our window's here, next our window could be here, we want to be able to take an element like this and remove it from the beginning. And we want to be able to do that in O of one time, which is why we need a queue. So let me quickly just run through this last example. So we have our first window over here, 8 and 7. So we add 8 to our queue. Then we look at 7. Well, 7 is not greater than 8, right? That's just not true. So we're allowed to add the 7. We only want to remove smaller elements if they exist. But in this case, that's not true. So we add the 7. And notice how these values are in decreasing order. We have 8 and then we have a 7, right? They're in decreasing order. So what that tells us is since we want the max value in our sliding window, we can just look at the leftmost value in our deck and then add that to the output. So I'm going to add 8. For the first sliding window, the max value happens to be 8. Okay, now the next sliding window, we have 7 and we have 8. Okay, the first thing to notice is that the 8 is no longer in bounds. So we got to pop from over here, right? And we want to do that efficiently, which is why we're using a deck. But so before we add anything, we pop. Next, we see the 6. Well, 6 is not greater than 7. That's not true. So we're allowed to put a 6 here to keep this in decreasing order. And now the max value in this window is 7, which is the leftmost value in our deck. So we add it to the output. And lastly, we look at the last sliding window, which is these last 2 elements. And we know that the 7 is no longer in bounds, right? So from the leftmost position, which is this, we pop from our deck. We make one last comparison, right? We just added a 9. Let's take a look. Is 9 greater than the top value of our stack? Is it greater than 6? It is. What does that mean? That means we have to pop from the top of the stack, the rightmost position, or rather the queue. I don't know how many times I said stack, but we're going to pop from the rightmost position in our queue. And now we are allowed to take the 9 and append it to our queue. So we add the 9 now. We know that this is the leftmost position in our queue, and we know that in this window, 9 is the maximum. So we did this correctly, right? So we can take the 9, add it to our output. So this is the result that we're looking for. And I hope this demonstrates a few of, like, when you actually run through examples, it shows you like what you need to know. It shows you why we're using to put a set to 0. And we're also going to have a queue. In Python, we can do collections.deck. And so we're going to run this until our right pointer is no longer in bounds. So while right is still in bounds. So we want to our queue, we want to be able to append the value, this value, right, R. And instead of doing nums of R, I'm just going to do the index itself. So this is going to contain indices, because we know we can take an index like R and then easily find the number that it maps to by just taking nums of R, right? But before we're even allowed to append a value to our queue, we have to make sure that no smaller values exist in our queue. So while the queue is non-empty and the top value in our queue, or the rightmost value in our queue, is less than the value that we're inserting, nums of R, which is the current index we're at. So while smaller values exist in our queue, we just want to pop from the queue, just remove values while that condition holds. And only after we do that are we allowed to add the new value to the queue. We also, if the left value is out of bounds, then remove the left value from the window. So if our left index, left, is currently greater than the leftmost value in our queue, then we can pop from the left of the queue. So basically, we know left and right represent our window. So if our window is out of, if this value, the leftmost value in our queue, is out of bounds of our window, we're going to remove that. We have to remove that. And this part is kind of an edge case. Since we are starting at our window being left and right both being at 0, we have to check that our right plus our window is at least size k. So if we want to update the output, we have to make sure our window is at least size k. So that's basically what I'm doing here. And for each iteration of the loop, basically for each window, we want to append our output with the maximum. So we know the maximum is the leftmost position in our queue. And we want not the index, but we want the actual value itself. Don't forget, like me, to update your pointer. So we know right is always going to be incremented. So at the end of our loop, we can increment right. Left, though, is only going to be incremented once our window is at least size k. So we're going to put that inside of this condition. And now the only thing left for us to do is return that output. And it works. And we know that this is the most efficient solution, with the time complexity being linear and the memory complexity also being linear, because we are using a data structure, our queue. So I hope this was helpful. If you enjoyed, please like and subscribe. Q. And the reason is because our Q is always going to be in decreasing order, which this next example is going to demonstrate. And the reason we're using a queue rather than a stack is because we want to be able to add and remove elements from the beginning in O of one time. But not only that, as our window shifts, like for example, our window's here, next our window could be here, we want to be able to take an element like this and remove it from the beginning. And we want to be able to do that in O of one time, which is why we need a queue. So let me quickly just run through this last example. So we have our first window over here, 8 and 7. So we add 8 to our queue. Then we look at 7. Well, 7 is not greater than 8, right? That's just not true. So we're allowed to add the 7. We only want to remove smaller elements if they exist. But in this case, that's not true. So we add the 7. And notice how these values are in decreasing order. We have 8 and then we have a 7, right? They're in decreasing order. So what that tells us is since we want the max value in our sliding window, we can just look at the leftmost value in our deck and then add that to the output. So I'm going to add 8. For the first sliding window, the max value happens to be 8. Okay, now the next sliding window, we have 7 and we have 8. Okay, the first thing to notice is that the 8 is no longer in bounds. So we got to pop from over here, right? And we want to do that efficiently, which is why we're using a deck. But so before we add anything, we pop. Next, we see the 6. Well, 6 is not greater than 7. That's not true. So we're allowed to put a 6 here to keep this in decreasing order. And now the max value in this window is 7, which is the leftmost value in our deck. So we add it to the output. And lastly, we look at the last sliding window, which is these last two elements. And we know that the 7 is no longer in bounds, right? So from the leftmost position, which is this, we pop from our deck. We make one last comparison, right? We just added a 9. Let's take a look. Is 9 greater than the top value of our stack? Is it greater than 6? It is. What does that mean? That means we have to pop from the top of the stack, the rightmost position, or rather the queue. I don't know how many times I said stack, but we're going to pop from the rightmost position in our queue. And now we are allowed to take the 9 and append it to our queue. So we add the 9 now. We know that this is the leftmost position in our queue, and we know that in this window, 9 is the max.